Hello everybody. So in this video we're going to continue with chapter 14, 14.5 specifically, integration by method of partial fractions. So in this section we will integrate rational functions with polynomial denominators. For example, if we want to find the definite integral x plus 1 over x squared plus 5x plus 6, we first decompose the integrand into partial fractions. So this is in section 2.6 of the book if you want to review it. And then the integration process is straightforward. So we have that x plus 1 over x squared plus 5x plus 6 is equal to a over x plus 2 plus b over x plus 3. So obviously, if we factor x squared plus 5x plus 6, this is the same as saying x plus 2 times x plus 3. That's where we get this from. But then we have to solve for a and b. So how do we do that? Well, normally, because these two are equal, we would have to multiply this times this to get the denominator. And then to get the numerator, we would have to cross multiply. So that implies that x plus 1 should equal a times x plus 3 plus b times x plus 2. So since we want to solve for a and b, and not really for x, we can take advantage of the fact that we have x on both sides of the equation. So that means that this equality has to be true for any value of x. So we can use an x that helps us get rid of one of these variables. So if we say x equals -2, we can get rid of b and solve for a. So let's plug in -2 for x, and we're going to get -1 is equal to a plus b times 0, right? I'm just plugging in the -2 for x. So that means that a is equal to -1. So we found a. Now we're going to solve for b. So again, we have x plus 1 is equal to a times x plus 3 plus b times x plus 2. So we can conveniently say x equals -3 and then substitute. And we're going to get -2 is equal to a times 0 plus b times -1. So then that means that b is equal to 2. So now we're ready to solve for this integral here, because we can rewrite it as -1 over x plus 2 plus the integral of 2 over x plus 3. And then this is straightforward because all we have to do is use natural logarithm. Notice that this is the same. Integrating this would be minus natural logarithm of the absolute value of x plus 2 plus 2 times the natural logarithm of x plus 3. And then let's not forget, plus a constant c. So in the next slide, we're going to take a look at a couple of examples of other situations. So first we have the case of repeated linear factors. If the denominator of the rational expression contains repeated linear factors, then following our discussion in the introduction, the process is as follows. So here we have this example where there's a polynomial that is being divided by x minus 1 cubed. So this is the repeated linear factor. This times 2x minus 5. So in these cases, we have to consider all the possibilities with linear factors. We would have to consider x minus 1 cubed, x minus 1 squared, and x minus 1. And then finally, 2x minus 5, which comes from here. So this is what we would have to solve in this case, right? We'd have to find a, b, c, and d. Now notice that it may turn out that any of these numbers could be 0, especially b and c. Okay, so the next case is when we have irreducible quadratic factors. If the rational expression we are decomposing contains irreducible quadratic factors in the denominator, then the numerator could have a linear and or a constant term. So for every irreducible quadratic factor in the denominator, we will need a linear term and a constant term in the numerator. So what does that mean? Well, for example, if we get this case here where we have x minus 1 squared, we know that this is a repeated linear factor, so we know what to do. We see it here. But in this case, this is irreducible. We cannot reduce this by factoring. So then that would require an expression in the numerator, like this one, that would have a linear factor and a constant term. So this is the linear factor and this is the constant term. So then we would have to solve for A, B, C, and D. In the following slide, you're going to see a few cases of partial fractions. First, when the denominator is quadratic, this is the case we saw first, and it's when you have a quadratic denominator that factorizes into two distinct linear factors. So you can see this, they're distinct. So this is the case where you get A over the first linear factor plus B over the second linear factor. Then we also saw the case where the denominator is quadratic, but it factorizes into repeated linear factors. And then you can see that that can be split into this here. You have this expression where you repeat the squared factor that you had in the denominator, but you also have to take into consideration the other case where it might just be linear. And then again, we solve for A and B. And finally, we have another case where the denominator is cubic and it factorizes into three distinct linear factors. Also, in every case, the numerator is either constant, linear, or quadratic. So notice that this one we would split into three fractions, and we would have to solve for A, B, and C. Very well, so next we're going to work on example 14.23, and it says find the indefinite integral. And it's the case where we need to split this up using partial fractions. So notice that the denominator here is equal to x plus 2 squared. So this is a case of repeated linear factors. So we can rewrite 3x minus 1 over x squared plus 4x plus 4 as a over x plus 2 squared plus b over x plus 2. And then we just solve for a and b. So notice that if we were to do this sum, we would have to multiply this expression here times x plus 2 in order to be able to do the sum. So that means that 3x minus 1 should equal a plus b times x plus 2. So we're going to get that 3x minus 1 is equal to a plus bx plus 2b. And we're going to rearrange this. So 3x minus 1 is equal to bx plus a plus 2b. So we're going to compare both sides of the equality. So notice that on the right-hand side, the coefficient of x is b, and on the left-hand side, the coefficient of x is 3. So no doubt that b is equal to 3. So we have b now. And then we also have that a plus 2b must equal -1. But we already know what b is, so that means that a plus 2 times 3 is equal to -1. So this would be a plus 6 is equal to -1. Therefore, a must be -7. So now we're ready to solve. So we said that a is equal to -7 and b is equal to 3. That means that we can rewrite this integral as the integration of -7. And let's recall that this was x plus 2 squared. And then for b we got 3, so this plus 3 over x plus 2. And then here the integration is quite straightforward. Okay, so notice that we can rewrite this as minus 7 times the integral of 1 over x plus 2 squared. And then this is the same as 3 times 1 over, or the integral of 1 over x plus 2. So if we do use substitution for this one, we're going to get that this is the same as 7 over x plus 2. And then this to the right would simply be 3 times the natural logarithm of the absolute value of x plus 2. And then let's not forget plus c. Very well. So next we have example 14.24, where they want us to find this indefinite integral. Notice that we can rewrite this expression here as 2 over x times x squared plus 2x plus 2. And then notice that this is irreducible. So that means that we can rewrite this as 2 over x squared plus 2x squared plus 2x. We can rewrite it as a over x plus what we would have in the denominator would be irreducible, right? X squared plus 2x plus 2. And then since this is quadratic, this here is quadratic, we have to have a linear term and a constant. So we would need to have bx plus c. And now we can solve. So notice that in order to add these fractions, we would have to multiply this times this and then cross multiply, right? So that means that 2 is equal to a times x squared plus 2x plus 2 plus x times bx plus c. So we're going to expand this and then compare both sides again. So I'm going to rewrite this on the left-hand side. So we're going to get that ax squared plus 2ax plus 2a plus bx squared plus cx. And this is equal to 2. Okay, so let's put together similar terms. So notice that this and this are similar terms. So that means that a plus b times x squared, and then we have this and this, right? So that's going to imply that this plus 2a plus c times x plus 2a is equal to 2. So notice that this here does not have any terms that are quadratic or linear, but only constant. So we get that from here. This implies that a is definitely going to equal 1. We also have these cases here. They have to cancel out. So that means that a plus b must equal 0, and that 2a plus c must also equal 0. But since we know the value of a, we can solve here for b, because 1 plus b is equal to 0. Therefore, b is equal to -1. And then here, we have that 2 times 1 is 2, so 2 plus c is equal to 0. Therefore, c is equal to -2. And now we're ready to substitute and solve the indefinite integral. So we said before that this expression here could be rewritten as a over x plus bx plus c over x squared plus 2x plus 2. But we already found that a is equal to 1, b is equal to -1, and c is equal to -2. So that means that we can rewrite this expression here in partial fractions as 1 over x, and because these two are negative, I'll just write it as minus x plus 2. And this, of course, over x squared plus 2x plus 2. So now we can integrate this. And this one to the left is easy to integrate because it's just going to be the natural logarithm of x, natural logarithm of the absolute value of x. So that's done. But we have to deal with this. So notice that if we attempt to do u substitution, it's not going to work. Because if we say, well, u is equal to x squared plus 2x plus 2, then the derivative of u should be 2x plus 2 dx. And we don't have 2x plus 2, we have x plus 2. Well, we might multiply by 2, but if we multiply this by 2, we're going to get 2x plus 4, so that's not going to work. So how can we make this work? Well, we can do a little trick here, because since we need to get 2x plus 2, if we had x plus 1 here, then we could do the integral. So notice that x plus 2 can be rewritten as x plus 1 plus 1. That is perfectly allowed, perfectly valid. So what does that imply? Well, that means that we can rewrite this expression here as, let's write it as x plus 1. So this is minus the integral of x plus 1 over x squared plus 2x plus 2. And then this plus 1 here, we're going to write it separate. We're going to separate it. But we have to take into consideration that there was a minus in front. So let's write this as minus 1, or the integral. Let's not forget the right notation. Minus 1 over x squared plus 2x plus 2. Okay, so now we're ready to fix this problem, right? Because we need 2x plus 2 up here. I could multiply this by 2 and this also by 2. So that means that this integral, since we now can use substitution, it would simply be minus 1/2 times the natural logarithm of the absolute value of x squared plus 2x plus 2. But we're still left with this problem here because this over here is obviously not the derivative of this, so we cannot do u substitution. So in this case, it's useful to manipulate this expression and try to get something that we can solve with inverse trigonometric functions. Notice that we can rewrite this as minus the integral of 1 over x squared plus 2x plus 1 plus 1. And notice that this is a perfect square, so we can use completing the square in order to solve this problem. So we're going to get that this is equal to the integral, and let's not forget the notation. I keep forgetting. So this is going to equal minus the integral of 1 over x plus 1 squared plus 1. And notice that with this case, we can use the inverse of tangent or arctangent. So we have a solution, because this would simply be minus the arctangent of x plus 1. So we have the final solution. This is going to equal the natural logarithm of the absolute value of x minus 1/2 the natural logarithm of the absolute value of x squared plus 2x plus 2 minus, I write it over here, minus arctangent of x plus 1, and let's not forget plus c. Very well, so now we are on example 14.25, which will be the last one on the video. And it says, find the following indefinite integral. So in order to use the method of partial fractions, we're going to have to factor the denominator. First, we're going to try to find zeros by analyzing the last term, or the constant, and the first coefficient, right? So we compare the possible divisors of -6, which are plus minus 1, plus minus 2, plus minus 3, and plus minus 6. We would have to divide these by the possible divisors of the first coefficient. So plus minus 1, plus minus 2. So all the possible combinations here would be plus minus 1, plus minus 1/2, plus minus 2, plus minus 3/2, and finally plus minus 3. So in these cases, I like to test the whole numbers first. So I'm going to test plus or negative 1. Although it's easy to see that positive 1 won't work, because if we get all of these positives, that would be 11, 18 minus 6. So that doesn't work because it gives us 12. And negative 1, negative 2, and negative 7 would be negative 9, plus 9 would be 0, minus 6, negative 6. So that doesn't work. 2 won't work because then all of this would be positive here. And this would all be positive, and then just minus 6 won't work. So let's try negative 2, which I suspect will work. So let's do 2 times negative 2 cubed plus 9 times negative 2 squared plus 7 times negative 2 minus 6. So this is going to be negative 16 plus 36 minus 14 minus 6. And this obviously gives a 0. So that means that negative 2 is a 0. In other words, x plus 2 would be a factor. Let's use synthetic division to find the other factors. So let's use negative 2 and then grab the coefficients from the original polynomial, which are 2, 9, 7, and minus 6. So we bring down 2, negative 4, add gives us 5, negative 10, add gives us negative 3. This is 6 and 0. So this means that this will then be 2x squared plus 5x minus 3. And then finally, because this is quadratic, we can do it or we can factor through inspection. And notice that it's going to be 2x minus 1 times x plus 3. So that means that we're ready for the next step because we have found the factorization of the denominator, right? It's going to be this here, this times x plus 2. So we will be able to use the method of partial fractions. So we have obtained that this is equal to a, well, that would be the integral, but let's just talk about this part here without the integral. We're only looking at the fraction. So this would equal a over 2x minus 1 plus b over x plus 2 plus c over x plus 3. If we had to add these three fractions, we would need to multiply the denominators, but also we would need to multiply a by this and this, b by this and this, and c by this and this. So that means, that implies that 5x squared plus 16x plus 17 has to equal a times x plus 2 times x plus 3 plus b times the other two denominators that are not dividing b, right? So that would be 2x plus 2x minus 1 and x plus 3. And finally, plus c times 2x minus 1 times x plus 2. So we're going to expand this and then we will compare both sides of the equality. So this is going to equal a times x squared plus 5x plus 6 plus b times 2x squared plus 5x minus 3 plus c times 2x squared plus 3x minus 2. And then we're going to expand all this, right? So this is going to equal ax squared plus 5ax plus 6a plus 2bx squared plus 5bx minus 3b plus 2cx squared plus 3cx and minus 2c. Okay, and then finally, if we rearrange all this and add similar terms, notice that we would get that a plus 2b plus 2c, right? I get that from here, here, and here. So I'm adding all the quadratic terms. So this times x squared plus 5a plus 5b plus 3c times x. Notice that I get that from here, here, and here. And then finally, plus 6a minus 3b minus 2c. This would be the constant part. So we have a constant part, we have a linear part, and we have a quadratic part. So all we have to do is compare that to this, right? And comparing that, we have then that a plus 2b plus 2c should equal 5. We have that 5a plus 5b plus 3c should equal 16. And we have that 6a minus 3b minus 2c should equal 17. So we get a system of linear equations with 3 unknowns and 3 equations. So this is solvable. And if you do it, you're going to get that a is equal to 3, and that b is equal to -1, and that c is equal to 2. So in a problem that is as long as this, you're probably going to be allowed to use the calculator for this instance here. But if not, you know that you can do this with matrices or elimination. We've done this before. So now we're ready to solve because we have that original integral, which I erased here a little bit. But this original integral here would then be equal to, let's see, we have to be careful. This one would be equal to 3, the integral of 3 over 2x minus 1 dx minus the integral of 1 over x plus 2 dx. And then we said that c is equal to 2. So this plus 2, the integral of 2 over x plus 3. So notice that this one and this one are ready for integration because we have u and the derivative of u. But here we have a problem because this 3 does not work for us. We need a 2. So let's just put this 3 out here and substitute it with a 2 for now. But we can't just do that, right? We also have to divide by 2. So there we are already, because this, if this is u, this is obviously the derivative of u, right? 2 dx is a derivative of 2x. So we're done because this is simply going to be equal to 3/2 natural logarithm of the absolute value of 2x minus 1. That's not a straight line. There. Minus the natural logarithm of the absolute value of x plus 2. And then, well, this 2, we just write it outside, right? Because in order to do u substitution, we need a 1 here. So then this plus 2 times the natural logarithm of the absolute value of x plus 3. And then let's not forget plus c.